if we want to find the sum of the angles on the interior of a polygon, we could actually use the same sort of approach that we did back in the last section talking about Euclid's theorem, where we would end up having to deal with even more transversals. In those cases, we'd have even more lines intersecting and cutting across on both sides of the parallels. So getting past anything even worse than a rectangle, it would become a bit of a mess. It's not really worth getting into in very much detail. Just know that the same sort of geometry that worked there can work more generally and leads towards a formula that we have where if we've got an n-sided polygon, then the sum of its interior angles is going to be n minus 2, quantity multiplied by 180 degrees. So for a triangle, that is for the case when n is equal to 3, that would end up being n, which in this case I should actually write out, is equal to 3 minus 2 times 180 degrees. 3 minus 2 is 1, so we just get 180. And then from there, if we talked a little bit more generally, we talked about, say, a pentagon, just for comparison. A pentagon, as hopefully we remember, has 5 sides. That's what the name says here. We use a simple, I can't remember if this is Latin or Greek etymology there, penta, 5, gon, sided. So what we get there, 5 minus 2 times 180 degrees, would in this case be 540. You can use this for any number n of sides to your heart's content. No matter how many sides we have, this idea still works. This idea still gets us what we're looking for. So we can use this to talk about a special pattern we get in certain shapes, a special pattern we can see with shapes being brought together, called a tessellation. And that's what we're going to finish this week's material looking at.